Hi, my name is Saul Boucher. I'm here from Carnegie Mellon University to present lightweight preemptible functions, joint work with Anuj, Kalia, Dave Andersen, and Michael Kaminsky. It's rare that a program only has one task to perform over the course of its execution. And one way that it might seek to schedule multiple tasks is by performing them in sequence. In this example, the program switches to a task shown in orange that is time sensitive. It would be nice if there were an easy way to instruct it to do so at a certain time. And ideally, this mechanism would be lightweight, that is, low overhead and cheap, and it would run the preceding code preemptibly. That is, it would be able to interrupt it at any arbitrary point. Some reasons this might be useful are to bound the resource use by the application, balance the load of different types of tasks on the system, or meet a deadline, such as in a real-time system. In this talk, I'll focus mostly on the latter use case, but our findings are relevant to the other ones as well. More generally, what we're talking about here is giving the programmer the ability to retain control over the CPU, allowing them to interrupt arbitrary unmodified code, while introducing minimal overhead in the common case, supporting cancellation, and maintaining compatibility with the existing systems stack. I'm going to start by talking about why the abstractions in our current system stack are ill-suited to this problem. And we'll start with the simple function call. Let's imagine that in the preceding region of this program, we make a function call. The thing is, functions are abstractions. The caller is not intended to have to read the implementation and understand what the function does. But that also means there's no guarantee that the function will return control back to the calling code in a timely fashion or even at all. Generalizing a bit, there are two main approaches to multitasking: cooperative and preemptive. In cooperative systems, code that is being interrupted is responsible for handing that control back, whereas in preemptive systems, it is externally interrupted. Historically, this is roughly aligned with the trade-off between the competing objectives of lightweightness and generality. Let's take a look at futures, a abstraction that has appeared in a number of modern languages. They're cooperative and usually implemented by creating lightweight userland threads and scheduling them with a language runtime. And one future can depend on another's result. When that happens, the compiler inserts a yield point so that if the dependency has not finished, the dependent future will yield. But again, the fact that a function is an abstraction poses a difficulty for us. It might be implemented in a different language, for example, in which case the compiler wasn't able to put yield points in it. Or maybe it performs a task that is not amenable to yield points. For example, it might perform image decompression, which is compute bound. Furthermore, image decompression exhibits this property that its time bound is unpredictable because the output buffer could be orders of magnitude larger than the compressed representation of the image. So the cooperative nature of futures mean they can't provide the kind of general purpose interruption we're looking for. We might instead seek to use a kernel thread. So instead of performing an image decode, for example, and then running our orange time-sensitive task, we could instead do the image decode on a separate thread and wait until the particular switchover point to do our time-sensitive task on this thread. The trouble is there's actually no guarantee that our task will start on time. Imagine the kernel schedules both of these things onto the same CPU core. Well, After timeout goes by, it may well decide to schedule more decoding. A related problem that often arises in production systems is that there'll be some SLA to meet. So in this example, it looks like we're actually going to miss our SLA if we start on this time-sensitive task when this diagram shows. Instead, we're going to probably have to spend less time on the preemptible portion. And that means we may not finish it. If it's really important, though, that we get the orange region done, that's a sacrifice we're going to have to make. And it would be nice if we had a way to cancel the work we've done on the other section so far. The trouble is with the process or with the thread model, it's actually hard to do that cancellation. So here we've spawned a second thread to perform the preemptible part of the work. But imagine that thread calls malloc, for example. As you may know, malloc uses a shared heap region that is used by multiple threads, and so therefore it takes a lock. Now if we cancel that thread and another thread tries to call malloc, it could deadlock. It turns out that there's moderate overhead for spawning kernel threads, about 30 microseconds of critical path latency. So we can eliminate kernel threads because of their poor ergonomics and lack of cancellation. Now, we might instead seek to create an entire process. So here we've created one for the preemptible function, but imagine this lifetime and ownership problem. So perhaps that preemptible function we spawn creates a shared object and passes a pointer out to the rest of the program. Now, if we cancel the process, or even if the preemptible function completes normally and the process wants to end, we could be left with a dangling pointer. So it's not clear where we should have allocated that object in order for its lifetime to be correct. Furthermore, there's relatively high overhead for creating a process, largely because the kernel needs to touch every page mapping in the memory space. And that takes about 200 microseconds on the critical path from end to end when you call fork. So we can eliminate processes because of their poor performance and ergonomics. And what these approaches have in common is that they require the programmer to sacrifice control by handing things over to an external scheduler. So looking back at our desiderata, actually one way that we could provide all of these things is to just add timeouts with function calls. That way, the programmer would be able to trust that they were going to get control of the CPU back. So that brings us to function calls with timeouts, which we call lightweight preemptible functions. They are faster than spawning a process or a thread, and that's largely because they run the preemptible code on the same kernel thread as the calling code. They're preemptible, specifically at the granularity of tens to hundreds of microseconds, which is an order of magnitude or so faster than most operating system schedulers will provide. On timeout, they pause, and they do that for two reasons. One, it's the lower overhead path, and two, it gives you the flexibility to later resume from where the preemptible function left off. And they're just that, functions. You take a normal function or closure that you want to run with a timeout, and you invoke it using our wrapper function. That wrapper looks a lot like pthread create, but it's synchronous. Let's take a look at an example. Here, we want to run the function func, passing it no arguments, and give it at most 400 microseconds to run. So we use our wrapper function launch, and then we save the result in this func state object. Assuming the 400 microsecond timeout was not enough for func to complete, func state is now a continuation object that can be resumed later on. This particular example pushes it onto a work queue. Then later on in the program, it might pop it back off and call resume. notice it can pass in a different time interval than it did before. Of course, the program might not have time to give it any more execution, and so it could cancel instead. One thing I want to highlight is that even though everything here is happening on the same thread, lightweight preemptible functions can introduce concurrency into your application. Here's an example. This preemptible function is a closure that captures the counter variable and increments it. It only gives it 1 microsecond to run, though, which may or may not be enough time. Then it increments the counter outside, checks whether the preemptible function had time to complete, and if not, allows it to run to completion, and then asserts the counter is equal to 2. Unfortunately, this program has an atomicity violation. Because the preemption could occur in the middle of that increment, we don't know what counter is going to be equal to at the end. And so this program is incorrect. Now, we don't seek to solve concurrency problems in this work. That's been the topic of a lot of the literature, but we do want to make sure that some of the concurrency tools you're used to still work here. And an example of one that does is the Rust compiler's support for borrow checking. And so if you try to compile that program in Rust, you'll get an error message similar to this that prevents you from doing so. Of course, if you really want to share this counter, you can use an atomic, or more generally, you can use any other synchronization mechanism such as a mutex. You just have to remember there's only one thread here, so you can deadlock by blocking. As a proof of concept, we've implemented libinger, a library that provides lightweight preemptible functions to C and Rust programs. And we'll take a quick tour of how that works. So here, we're launching a function and allowing it to run to completion. And when launch is called, it's going to switch to a new stack to run that function. When the function completes, it returns into some stub code that tears the stack back down. And then when launch returns, it does so to its caller, as usual, as if nothing out of the ordinary happened. Now, the reason we needed to do all that is that somebody might have passed in a timeout instead of allowing the thing to run to completion, in which case, periodically, we would have a timer interrupt asserted, and a timer signal would run to handle it. A timer signal handler would run to handle it. And that signal handler would check whether a timeout had occurred. If so, launch would resume but save that stack, meaning that later on, somebody could call resume to jump back into the handler and resume the function. Now, this means we have some state we need to clean up. If somebody calls cancel, we tear down that stack. We do not, in this paper, support cleaning up other state that may have been allocated by func, but we have some ideas that we present about how you could get started on that project. Now, you may have noticed that I described a mechanism whereby we had a periodic timer signal coming in, checking for a timeout each time. The reason we don't just use a single signal at the end of the preemptible function is that there's a warm-up effect on the signal arrivals. Of course, there are some ways we can improve this, and we talk about those in the paper. One is, depending on the timeout that's passed in, we can adjust the spacing between those signal handlers. And another is, for longer running preemptible functions, we can start the signals coming in toward the end. We've run some micro benchmarks to demonstrate the performance characteristics and found that launch and resume each has a cost of about 5 microseconds. Looking back at thread creation and process creation, that's an order of magnitude or 2 orders of magnitude better, respectively. Now, the slow operation currently is cancel, which takes an order of magnitude longer than fork. But that operation is not typically a critical path operation. You can, for example, use a separate Reaper thread to clean up that state. In order to demonstrate the performance of cancel in a real system, we took an image decoding problem where we were decoding PNG images, one of which was malicious. And we said, okay, there's a sort of 10 millisecond limit on how long we want to spend on this operation. So just running a decode without any enforcement of that timing, the malicious image took 2 orders of magnitude longer than to decode, even though the file was about the same size. Then we tried using a thread. And there are 2 interruption mechanisms for threads, but the asynchronous or preemptive one does not actually work. We talk more about that in the paper. Without that mechanism, we weren't actually able to use the thread to cancel at all. Then we tried fork, and we found that it was able to provide this sort of preemptible function execution with about a 400 microsecond overhead. And then trying launch, we got about a 100 microsecond overhead. And this was a whole end-to-end experiment with a separate Reaper thread for cancellation. So the fundamental challenge for preemptible functions is actually getting them to work on top of the existing system stack without breaking your existing code. And the reason that's tough is non-reentrancy. So imagine we have a program that calls 2 preemptible functions, and each of those preemptible functions calls the C stirtalk function. If you're lucky enough to have forgotten about stirtalk, it is a library function that allows you to split or tokenize a string. The first time you call it, you pass in the string and the delimiter, and then on subsequent calls, you just call it without that stuff, and it remembers what it's been doing so far. But of course, now we have these preemptible functions. We might interleave their executions, and so stirtalk could get all confused. Now, C already mitigates this sort of problem by giving a rule that signal handlers, because they interrupt the program's execution, cannot call non-reentrant code. The trouble is that preemptible functions kind of turn this on its head. So in their case, the rest of the program is the thing that interrupts the preemptible function. And that should mean that the rest of the program cannot call non-reentrant code. Obviously, this is not a restriction we can accept. So we need to provide some form of memory isolation, just like fork did, in order to truly provide safe concurrency here. And so the approach we go with is based on library copying. So we can view those stirtalk calls as transfers of control into the libc module. And we can make a copy of the library for each lightweight preemptible function and rebind the call sites. Now, if this looks a little bit expensive, you're right about that. But the good news is that we can reuse each copy as long as its preemptible function runs to completion and therefore doesn't leave it in an undefined state. In order to understand how we implement library copying, it's important that we first understand dynamic linking. So let's do a quick review there. Somehow this executable needs to bind stirtalk to the libc module. And the way that's done is that there is a structure called the global offset table in the program's process image. That is an array of a bunch of pointers. And the stirtalk call is really just a load followed by a jump. So what do we do if stirtalk is called from within a lightweight preemptible function? How do we reroute the call? Well, we've implemented a runtime called libgotcha that performs a process we call selective linking when it's loaded. So if this program calls stirtalk from within a time function, then it must depend on libgotcha. And when libgotcha is loaded, it makes a copy of the library for each lightweight preemptible function, creates a shadow GOT corresponding to that copy, and then points the GOT entry at itself. Then whenever a call goes through that GOT entry, a little assembly stub in libgotcha runs and decides which shadow GOT to serve it from. I'm glossing over some details here, but you can see the paper for more. Now, technically, we actually operate at the granularity of a libset, which is the full set of all a programmer's libraries. And that means that if we cancel a preemptible function, we have to unload and reload that entire libset. That's where the delay in cancel comes from. But take a look at the paper. We have some ideas about how to significantly reduce that. Now, that doesn't work for everything. For example, if we used it on malloc, we would end up with multiple heaps. And then we'd have the same sort of ownership and lifetime questions we saw in the fork discussion. So instead, we disable preemption, call the real malloc, and then immediately check whether we have run out of time during that allocation. If we haven't, we re-enable preemption and resume the program. Now, you may have noticed I didn't say anything about blocking system calls, and that's because we don't introduce any new support for those. Instead, we use a libc feature called SA restart when we create the signal handler. And that makes libc run syscalls in a loop. So when this syscall transfers control to the kernel and then later gets interrupted by a signal, libc will detect it and retry. A micro benchmark revealed that it takes about 12 nanoseconds of overhead to make a dynamic function call with libgotcha loaded. Now, that is only for exported symbols. And we compared it to the time for a basic fast library function and syscall, and found 65% and 30% overhead, respectively. Now, of course, we expect that most function calls and syscalls will take a lot longer than that, and therefore exhibit lower overhead. The expensive operation for us is global variable accesses. But the good news is that those are becoming rare. So even the erno variable in libc, it has disappeared. The Linux standard base now specifies that it should be served via a helper function. So finally, I'll wrap up by talking about preemptive userland threading. I don't have time to go through how we did it, but we created libturquoise, which is a modified version of the Rust Tokyo userland thread pool. And that resulting library is what we believe to be the first general purpose and backward compatible thread library that is both preemptive and implemented entirely in userland. And to evaluate that, we benchmarked the Hyper web server, which is the fastest performing one in the most recent Tech Empower benchmark. And we've bombarded that web server with compute-bound requests and measured the response time. And there were two classes of requests in the system: short requests that took 500 microseconds to process, and long ones taking 50 milliseconds. We varied the percentage of long ones in the mix, and we only measured the response time for the short requests. So looking at the median response time, we were graphing the latency of the short ones on the y-axis here, and the percentage of long requests in the system on x. So the vanilla Hyper system had pretty flat performance. When we introduced preemption, there was a little bit of decay going up to about 4.5% overhead at the 2% mark. But we didn't actually have to make any changes to hyper in order to run this. We just built against libturquoise instead of the native hyper thread library. But then we looked at the 99% tail, and we found that in the cooperative case, the short requests latency fell off immediately. The system just could not handle the presence of those long requests. Whereas with our preemptive system, it was able to hold it to a slow linear increase. And that's because it mitigated the effects of head of line blocking. In summary, we've introduced lightweight preemptible functions, which are function calls invoked with a timeout. They're a synchronous preemption abstraction that supports resuming and cancellation, is interoperable with legacy software, and has exciting applications in systems. Thanks for your attention. And if you have any questions, take a look at our paper or send me an email.